Hi. Look, in couple of videos that we went through over past few weeks, we've learned about derivatives. We've learned about analyzing how the function looks like using derivatives, finding maximum and minimum. But thus far, we said nothing about how this knowledge could be applied to economic problems. And this is going to be the topic of this video. And we're going to start with the most common issue in economics, which is finding maximum level of the profit. Okay, so let's start. Let's simply start by going about it from a theoretical perspective, and then we're going to move to an example that's going to show us how can we apply what we learned in on the example. Okay, so first, profit is usually denoted by pi. And look, in our simple example, we're going to consider the situation when profit can be expressed solely as a function of the level of production. So we've got that pi is profit, and Q is level of production. Okay, now how do we calculate the profit? Well, first we need to take into account all the money that the company is making. So total revenue. Total revenue here we will also consider as a function of quantity produced alone. So we've got the total revenue is denoted by TR. And please remember also that we can easily find total revenue because total revenue is nothing more than quantity sold times price at which this quantity was sold. Okay, so now we have everything the company makes, but company also needs to spend the money. So, in our case, we also need to introduce total cost. And we are also assuming that this total cost can be expressed as a function of level of production alone. We'll actually get a little bit more into details with total cost a little bit later. For now, let's just remember that TC is total cost. Okay, so now our task is to maximize the profit. We know how the profit function looks like. So what we do first? We of course use first order condition. First order condition is telling us to take the first derivative of profit with respect to quantity. We can denote it as d pi dq, but we can also denote it simply as pi of q prime. It doesn't really matter. Okay, and now look, we need to now calculate the derivative of what is on the other side. So we need to take first derivative of total revenue with respect to quantity and subtract from it the derivative of total cost with respect to quantity. Remember that even though we have no idea at this moment what is the specific form of this function, it does not prohibit us from expressing profit, first derivative of the profit, as a difference of the derivative of total revenue and total cost. Why? Because we actually proven that derivative of a difference is equal to difference of two derivatives. Okay, and look, of course, we need to now equalize this with 0. Because look, the point that is a candidate for either maximum or minimum is at a point where the value of the derivative is equal to 0. Okay, now let's consider for a second what we do have over here. Look, here we see that we've got first derivative of total revenue with respect to quantity. So, in other words, this expression is telling us by how much will total revenue change if quantity increases by some very small amount. And probably in your microeconomics classes, you've already heard a similar concept. This concept is marginal revenue. Marginal revenue is telling us by how much revenue of the company is going to increase, or in more general, change as level of production is increasing by 1 unit. So, actually, as it turns out, first derivative of total revenue is marginal revenue. So look, what we get over here is simply marginal revenue. And look, over here we have an expression that is telling us by how much total cost is going to increase if level of production of our company is increasing by some small amount. Again, you might hear a similar expression during your microeconomics class, because this is marginal cost. And again, marginal cost can be calculated as first derivative of total cost with respect to the level of production. So, now we have obtained the condition, the first order condition in terms of marginal revenue and marginal cost. And look, if I'm gonna move this expression to the other hand side of the equation, what I'm getting is famous marginal revenue equals marginal cost condition. That gives us a level of production for which company is maximizing level of the profit. And look, if we would have here, instead of general expression like marginal revenue or marginal cost, different expressions, some specific expressions, we would be able to solve this equation, and out of this equation we would find level of profit, level of production that would maximize our profit. We will denote this Q with asterisks. But look, there is a catch to it. If the function is complicated enough, we might get more than one level of the profit, this level of production that satisfies this condition. And look, at this moment, we do not actually know whether this is maximum profit or maybe a minimum profit, because the same first order condition is for both maximum and minimum. So, now, in the second part, we need to decide whether we found maximum, minimum, or maybe an inflection point. And this is what we're going to do right now. How are we going to do it? Well, we're going to simply use second order condition. So what do we do in the second order condition? Well, in the second order condition, we need to differentiate profit function for the second time. So we will have here d squared pi d q squared, or what is exactly the same thing, pi b's q. Okay, and now we need to just differentiate those expressions. Look, actually, because we do not have specific form of the function, we have just general form, all we can get here is dmr dq, so derivative of marginal revenue, and minus derivative of marginal cost with respect to a quantity. And look, now, because we only are interested in finding maximum profit, we need to do a couple things here. First, let me rewrite this again in a little bit different form. So as mr prime of q minus mc prime of q. And look, here we want two things. First, this is going to be a maximum if and only if the second derivative is lower than 0. But, as I said, look, here we can get more than one q. So what we put inside now the function, we simply substitute within this condition every possible q, and we are looking for the level of production for which this expression is actually negative. And look, again, I can transform this a little bit, and I'm going to get that out of this, that marginal revenue prime out of q with asterisk should be smaller than marginal cost prime with asterisk at this particular point. Now, this condition, if this condition is fulfilled, we already know that at this particular point, we can find level of production that maximizes level of a profit. But what are those two expressions? Okay, let's start with this. This is a slope of marginal revenue. How do we know this? Good. This is simply a derivative of marginal revenue. So it must represent a slope of marginal revenue. Now, what do we have over here? Over here, we've got slope of marginal cost. And look, even though in theory a lot of things are possible over here, but how does it look in practice? Marginal cost is an increasing function. What does it mean? If this function is increasing marginal cost, right? Then the slope of the marginal cost function is going to be positive. On the other hand, marginal revenue, in case of marginal revenue, when we have, of course, well-behaved demand, marginal revenue is either a decreasing function, or in a special case, it can be flat function. So look, this function, so the slope over here is either going to be negative or equal to exactly 0. So this condition, as long as some very basic rational assumptions are fulfilled, is going to be fulfilled as well. But of course, when we do an exercise on some problem, then we need to check this condition again. Okay, so now let me just point out what we should do at the very end. Look, once we have found level of production that maximizes our profit, we can find maximum profit. How do we do it? Look, we simply take the profit function that we had over here and we substitute optimal level of production, and this is the level, and this will give us the exact value of the profit, that the maximum value of the profit that can be achieved. Okay, so now that we know how to do it in theory, let's move for a second onto the example of how to do it in practice. Okay, so let's start by placing some okay, so our example goes like this. Demand function for some specific company product is given by 100 minus P. Then a total cost of the company is given by 1/3 cube minus 7 cube. Let's use lowercase q's. Square plus 111 cube plus 50. Okay, this specific form of the total cost is not coincidental, but about that a little bit later. Let's for now focus on the second part. Look, I just told you that this is the demand function. Look, what does the law of demand implies? The higher the price, the lower the quantity, right? How can I check if, in this case, this particular function conforms to this requirement? Look, it's actually very simple. I can calculate the derivative. Derivative here, dq dp, is simply equal to -1, right? This is a linear function. So what does it tell me? That when P is going up, so when price is getting higher, we are selling less. In this case, the relationship is exactly 1-for-1. But because this condition is met, we can be sure that this function can represent demand very, very well. Okay. Now, we've got total cost, but we still don't have total revenue. But we also remember that total revenue is equal to price times quantity, right? So, what can we do with this right now? Look, one thing I could do is to use Q from here, right? And place it over here, right? What would we have then? P times 100 minus P. And look, because we have total cost expressed in terms of quantity, we would be having inside the profit P and Q, which is not a very good idea. So this is a very bad way to go about it. But look, if we have the demand function, why not take this demand function and solve it for P? Look, this is really easy. All we have to do is to put P on the other hand side of the equation and Q on the other hand side of the equation. So we've got the P is equal to 100 minus Q. And now I can substitute inside, I can substitute this P inside the total revenue, and I'm getting that this is 100 minus Q times Q, which gives me 100 q minus q squared. Okay. So what should be our next step? Of course, now I can build profit function. So profit, which is equal to total revenue minus total cost, is given by. Of course, instead of total revenue, I'm writing this 100q minus q squared. And now, look, what I need to do is to subtract total cost. And look, this is a very common mistake. Remember, minus is in front of the entire total cost. So we need to change the sign in front of every component we've got over here, right? Because look, we can imagine it like minus 1 over 3q cubed minus 7q squared plus 111q plus 50. But of course, we get rid out of the parentheses over here. Let me just do it slowly. And what do we get? Look, still 100q minus q squared stays the same, but now we have minus 1 over 3q cubed plus 7q squared minus 111q minus 50. Right? I simply changed the sign of every expression. And look, now a good idea of what to do is simply to simplify this expression as much as we can. And we can do a lot of it. Well, expression with q cubed will definitely remain unchanged. Then we've got two expressions with q squared, so we've got that this is plus 6q squared. 100q minus 111q will give us a minus 11q, and then we just got minus 50. Okay, now that we have the profit function, because this is our profit function, right? What can we do? Like, now we need to just simply find the level of production for which this profit is going to be the highest. And of course, we need to start simply by calculating first order condition. So we start with first order condition, and it tells us to calculate the first derivative of the profit. So this is 3 goes up front, so we got negative q squared, then plus 12q minus 11, and we should equalize it with 0. Okay, so now we need to just solve this equation. And look, of course, we could use a quadratic formula for this, but this is really easy and there's an easier way around it. How? Look, for example, I can say, rewrite this expression as right? It's exactly the same expression, but what I can do now, look, out of the first part, first two, because this turns into those two, out of this part, I can take minus q out. So I get q minus 1. Then, out of the second part, I can take 11 out. And now look, because we have two identical expressions, I can take them out of the parentheses, and what I'm ending up with is q minus 1 times 11 minus q equals to 0. And look, out of this, right away we see that we will have two candidates. For maximum over here. First candidate is going to be Q equal to 1, and the second one, Q equal to 11. You know what? At this moment, let's not put asterisks. Why? We'll see. Okay, so look, what do we get out of this is that two possible levels of production can give maximum profit. But remember, one of them could be a minimum, one of them could be inflection point. So let's see what truly are. Okay, in this case, we of course need to resort to second order condition. So we calculate second derivative of the profit function, and what do I get out of this? So I'm differentiating that, and I'm getting that this is minus 2q plus 12. And look, at this moment, this is not telling me a lot, but now I can substitute the two values inside this second derivative and see which one is positive, which one is negative. I'm going to start with q equal to 1. Now, if q is equal to 1, then we've got that this is minus 2 times 1 plus 12, or simply 10. If second derivative is positive, it means we have minimum. Now, if now I'm going to substitute 11, so our second solution, I'm going to get that this is negative 2 times 11 plus 12, which is equal to negative 10. So it means that this is our maximum. So when level of production is equal to 11, we have maximum. And because here we have minimum, we should disregard this option. Okay, so what is the last thing we should do in this case? We know how much we should produce, right? But we should also be interested in how much money we are going to make on it. So we need to calculate maximum profit. So, of course, we're going to take the profit function and we're going to substitute inside the optimum level of production. So we will have pi out of 11. Okay, and look, this is our profit function. So what I'm going to do right now is simply substitute q's with 11. So I'm getting that this is negative 1 over 3 times 11 to the power of 3 plus 6 times 11 to the power of 2 minus 11 times 11 minus 50. Okay, so what am I getting out of this? So I'm getting negative 1 over 3 times 1,331. And look, over here, we've got 6 times 11 squared minus 11 squared, right? So this is 5 times 11 squared, which is 121. So, yeah, 5 times 121. And then at the very end, we've got minus 50. Okay, so now let's put all of these expressions into common denominator. So we've got that this is negative 1,331 over 3. Now plus, we will have here 5 times 161 121. But now if I want to put it into common denominator, I should multiply it by 3. So it's 15 times 121. So this is 1,815. And finally, out of this we will have minus 150 over 3. So, finally, if I'm gonna take this, subtract 1,331 and 150, I'm gonna get that this is 334 over 3, or simply 111 and 1/3. 111 and 1/3 is the value of the profit, maximum value we can obtain, and we are obtaining it when we produce 11 units. Okay, so look, we have learned now how to find maximum maximum profit, and we've actually discussed total revenue quite a lot, but we haven't discussed the cost. And look, this is what I wanted to do with you at this very moment. And look, I'm going to discuss with you 2 microeconomic relationships that you were already discussing in your microeconomics class, but now I'm going to show you the formal proofs that those relationships actually hold, and I'm going to show you, of course, how do they work. Okay, so the first thing we're going to discuss is short-run total product, or so-called Knight's curve, from the person who invented it. Okay, look, this is a graph. This is a graph that is relating the amount of labor, so number of workers the company can hire, to the total level of production, so total product the company can attain. And look, it was empirically shown that this relationship looks like this. First, level of production in the company increases faster than proportionally, and then it reaches, of course, inflection point, and it starts to increase slower than proportionally, and even after some level, some number of workers is hired, it reaches maximum. Look, this is all to the works of law of diminishing returns that you've heard about. And look, you can imagine it, like if there is a company, if this company has a certain amount of capital, so a factory plus some machines, then if the company at the beginning, for example, cannot hire too many workers, then each additional worker can actually, the workers, instead of doing 3 different tasks, each of them can specialize, and because of that, level of production is increasing faster than proportionally. You see, this part of the function is convex, right? So at the beginning, when we hire more and more workers, because instead of one worker doing 3 separate tasks, each worker can specialize. Now, level of production in the company increases more than proportion. Then, over here, something changes. Look, now that we have already many workers, they can no longer specialize, so each next worker is bringing less and less additional value to the company. Basically, at this moment, benefits of specializations are running slowly up. Now, at some point, we are getting the number of workers, let's call it, no, let's not call it at this moment, we will do it later. We have some amount of workers when we achieve maximum level of production this company can attain, having given amount of capital, of course. And now, look, this is a situation where we hire too many workers and actually they start to interrupt each other, or tasks are too divided between them and it doesn't make sense, so the level of production actually starts to fall. Okay, now, how will marginal product and average product look in this company? Okay, marginal product is, of course, first derivative of total product, this time with respect to labor, right? Because we are increasing number of workers in the company. So, even without calculating the derivative over here, we can basically guess how marginal product should look like. Okay, look. Here, we see that the function increases more than proportionally. What does it mean? Well, it means that over here, slope of the function is increasing. So, I'm sorry, I need one more point for this to work. So we see that over here, marginal product should be increasing, right? Marginal product measures the slope of this function, because derivative measures the slope of a function. So if here function is getting steeper, marginal product should be getting high. But look, here we have an inflection point, right? And what is happening over from this point on? The function increases, but less than proportion. What does it mean? It means that marginal product is still positive, but it starts to decline. And look, of course, at the point where function reaches maximum, marginal product must be equal to 0. And from this point on, it continues to become more negative. Okay, so this is marginal product. Now, another thing that we can calculate over here is average product. Average product is total level of production in the company per one worker. So how much on average one worker is producing. And look, I'm going to show you a graph of how it should look like. So this is average product. Without first explaining to you why. Look, of course it makes sense. Look, if here level of production in the company increases more than proportionally, then it means that for each additional worker brings more production. So on average, it should increase. At some point, it will get maximum, and then of course, as each worker is bringing less and less to the company, and at some point actually production starts to decline, average product should decline as well. But now look, in this circumstance, I draw it in a very specific way. Look, maximum over here is at a very specific point. It is at the point where marginal product is equal to average product. You might say, of course, that this is coincidence, but it is not. Let me now prove it to you. That this is how it needs to be. Okay, so look, what I want to do right now is to find maximum of the average product. So average product is function of total product, is a function total product divided, by labor. Okay, you might say, but we do not know how this function looks like, right? We don't know anything. How can we find maximum? As it turns out, it is not necessary. Look, let's go to first order condition. In first order condition, what I'm going to do here is to differentiate average product, right? With respect to labor. So I'm finding a derivative of total product divided by labor. Now, what rule we should use? Of course, this is a quotient of two functions. We should use the quotient rule. Okay. So we've got that this is first derivative of total product. I'm going to denote it as Tp prime to make it easier. Times L minus Tp times derivative of L with respect to L, which is simply 1, and we divide it by L squared. And look, this needs to be equal to 0 to ascertain that this is a maximum. Okay, so look, what did we get out of this is the total product prime times L minus Tp times 1 divided by L squared must be equal to 0. Now look, in this circumstance, we cannot get 0 by dividing this expression by anything, right? And we also cannot divide by 0, so we exclude, of course, the possibility of L being 0, giving us maximum level of production. So actually, we don't need this. Let me just erase it. Right? Now, this 1 next to total product is also not doing anything here, right? So let's get rid of this. And now, how will I call first derivative of a total product? Well, but this is nothing more but marginal product. Okay, so look, we've got a way simpler equation. But let's make it even more simple. We've got that MP, marginal product times labor, is equal to total product. Or, if I divide both sides by L, which we assumed is different than 0, we get that marginal product is equal to total revenue over, total product over labor, or what is the result that we wanted to get? Marginal product is equal to average product, because this is an average product by definition. So look, we got only from the first order condition that level of production of the company, that average level of production of the company is maximized at the exact point where marginal product is equal to average product. Okay, now let's repeat exactly the same exercise that we did here, but for a different function. Now, instead of having Shortrun total product, we're gonna have okay. Let's do it over here. We're gonna have Shortrun total cost. Okay. Now, I'm not going to do with you a specific derivation of the exact derivation of the total cost, but actually let me just point to you a couple of more interesting points about total cost function itself. Okay, first, total cost of the company, as you learned in your microeconomics class, can be divided into two parts. Into variable cost and fixed cost. What is the difference? Well, variable cost depends on level of production. Okay, so now, fixed cost, on the other hand, doesn't depend. Variable cost depends. I'm sorry. Depends. Oh yeah, it is depends. Doesn't depend on the level of production. So, example of a fixed cost. Look, if you are renting a factory, it doesn't matter if you're producing or not. You need to pay the rent. You need to pay your accountant. And it doesn't really matter if your company produced one car this month, 2 cars, or 500 cars, you still need to pay accountant the same amount. Now, variable cost is that if you're producing cars, it means if you're going to produce more cars, you're going to use more parts. Of course, this is part of variable cost. If you want to produce more cars, you're going to hire more people. So this is variable cost. Okay, so knowing this, how should I draw short-run total cost? Look, first, I should start with fixed cost. Because look, fixed cost is something we need to pay even if we do not produce, right? So I'm going to start with fixed cost over here. And now, the rest of the function is going to look like this. It will be associated with this part of that short-run total product, but it will be actually an inverse function of this part. What does it mean? It's going to look like this. I do not have time to give you a full long explanation, but think about it. Look, if we want to produce more, we need to hire more people. If we are hiring them at the beginning, we see they are getting more and more productive, right? So it means that if we produce at the beginning, the level of cost is increasing slightly because we hire a little more people, and we are producing way more. But then, as you see from this point on, which is again an inflection point, we get that the more we produce, the more people we hire, the less each one is bringing to the company. So this time, actually total cost is increasing faster than proportion. And look, so we see here the function is increasing concave, increasing convex. And look, this is usually the case when we have inverse function. What used to be convex becomes concave, what used to be concave becomes convex. Yeah. Now, okay, and look, knowing this, again, I can, even without doing any additional work, deduce how marginal and average cost is going to be. So, look, we already said that marginal cost is nothing more but the first derivative of the total cost with respect to production. Okay, and look, what do we see over here? If I want to put marginal cost over here. Now, at the beginning, look, fixed cost is fixed, right? If I differentiate a constant, which is fixed cost, it's going to be 0. It's not going to affect how the marginal cost should look. But look, what we have over here is actually, we see that fixed, what we see over here is that total cost is increasing, but it's increasing slower and slower and slower. And look, what is the slope of the function at inflection point? It is 0. So actually, marginal cost over here is going to be falling because look, the slope of the function is getting lower and lower and lower, and then it is 0, right? So if it is 0, of course, value of the derivative must be 0. And look, from this point on, the function starts increasing faster and faster and faster, which means that marginal cost is getting higher and higher and higher. Now, average cost is going to be equal to total cost divided by quantity, right? Now, how does average cost look like? Well, again, I can draw this here, and here we have minimum. Again, I can just explain this to you because it doesn't require much imagination to understand it. Look, if here, with level of production, cost is increasing slower than proportionally, then of course, average cost, which is total cost divided by quantity, will be falling. But since a specific point, as on the other hand side of the inflection point, on the right side of the inflection point, we get total cost that is increasing faster and faster, we expect that average cost is going to be increased. Now, but why is that the marginal cost, average cost is getting the lowest value at a point when marginal cost intercepts with it. And look, again, I can just simply prove it to you using first order condition, just like we did with total product. So look, I'm taking margin, I want to take with first order condition, I want to calculate first derivative of average cost with respect to quantity. So, what am I doing now? I'm differentiating total cost with respect to quantity. And if I'm doing this, again, I need to use the quotient rule. And now look, first derivative of total cost is marginal cost times quantity minus total cost times first derivative of quantity, which is 1, divided by quantity squared equals to 0. And look, again, This one doesn't change anything. Q is not introducing anything to us, so we get marginal cost times quantity minus total cost is equal to 0. So marginal cost times quantity equals to total cost. And finally, we get the marginal cost equals to total cost over quantity, or as we would prefer to put it, marginal cost is equal to average cost. So again, we see that average cost takes the lowest possible value at a point where marginal cost and average cost are equal to one another. Okay, this is it about applications of derivatives and maximization generally, or minimization to economic problems. In the next video, we're gonna start something a little different. Thank you for your attention.